What's up, guys? It's me, Sir Ernest, and today we're going to solve an example on how to calculate center mass of a hemispherical shell. So if we have a hemispherical shell, it means that the inside part of this hemisphere is empty. So the mass is concentrated on the shell, on the surface. So this is an example of a two-dimensional problem. And in this case, the volume element that we're going to use here is not a disk, unlike what we used in a solid hemisphere, but instead, you're looking at a circular strip. So a circular strip would look something like this. Okay, so this will be your circular strip. The thickness of the circular strip would be determined later. So if we're going to draw it in this two-dimensional view of the hemispherical shell, this would look something like this. So let's define the following parameters. So let's say the radius of the disk is r, and then the distance from the xy axis would be z. But instead of using the thickness to be dz, what we're looking at is the arc length that this part takes. If we're going to zoom in here, this will be the line joining these two parts, and another line here. So this would be theta. That's the angle from the xy axis to this segment. The arc element would be d theta. The specific length would be dl. This line and this line is actually the radius. This will be your radius A. The area element, or the area of this strip ds, this is now equal to the circumference of the strip times the thickness of the strip. So this is C dl, where C is the circumference. And the circumference of the strip would be equal to 2 pi r. So this becomes 2 pi r dl. So from here, we can see that dl is actually equal to the product of this infinitesimal arc element d theta times the radius a. So this becomes a d theta. Therefore, the area of the surface element will now be equal to 2 pi r a d theta. Moreover, the relationship between z, a, and r will use the Pythagorean theorem. So this will now be equal to 2 pi times a squared minus z squared to the 1/2 times a d theta. So since theta is related to a and z, since sine theta is equal to z over a, so therefore, if you're going to take the differential of this, we now have cosine theta d theta, and this is equal to 1 over a dz. If sine theta is c over a, cosine theta is equal to r over a. Again, from this triangle, or from this triangle. So therefore, d theta will be equal to dz over r, or a squared minus z squared to the 1/2 dz. So we're going to substitute this here to get ds. So again, by symmetry, the x and y components of the center mass is 0. So we're now left with ZCM, which is equal to integral of rho z ds divided by integral of rho ds. So here we can cancel rho, and then we can substitute our earlier results. So this becomes integral of z ds would be 2 pi. Okay, sorry about that. This should be minus. So this becomes d theta would be 1 dz over r. So that means this will cancel with this. So you're now left with 2 pi a dz. So this is 2 pi a dz. And then the integration will be from 0 to a. So this is 0 to a. Below, the denominator, we now have 2 pi a dz. So again, ds would be 2 pi a dz. Okay, so this is from 0 to a. So here we can now again cancel 2 pi a. So this becomes z dz. Then integrate. So that becomes z squared over 2. Then evaluated from 0 to a. And then in the denominator, we have z evaluated from 0 to a, which will yield the result to be equal to a over 2. So that's it. That's the center mass of your semi-spherical shell. If you're going to locate it here, it should be somewhere at the middle of the z-axis from 0 to a. So somewhere here. So this is your center of mass. That's it. That's the center mass of hemispherical shell, wherein the x and y component is equal to 0, where the z component is at a over 2. So I hope you learned something today. Thank you guys for watching. I'll see you again. Bye-bye.